have a disc, but the disc has a circular hole cut from the center, and that's called an annulus. It has an inner radius of R1 and an outer radius of R2. The disc itself has a uniform positive surface charge density given by sigma, where we know that that would be total charge divided by total area. First question we're asked to find the total electric charge on the annulus around the disc. So if we're going to find total electric charge and we know the surface charge density, well, we know that charge equals the density times the area. How do we find the area? Well, that gets us thinking about how do we treat this annulus. Let's think first, what if we had a solid disk with radius R2? Do the best I can, it's not a super drawing. So what if we had this disk with R2? Then that looks a lot like this disk, but this has a center cut out of it. So we'll have to take this disk and we'll have to subtract a smaller disk from the center. And that smaller disk would have radius R1. So this guy would be a solid. This guy would be a solid. If we take this, take away this, we end up with this guy. So to get that area, we'll do the area of R2, take away the area of R1. So the area of disk with radius R2 is pi times R2 squared. And the area of a disk with radius R1 would be pi times R1 squared. Then to simplify our result, we'll just haul the pi out front. We've got sigma times pi times R2 squared minus R1 squared. So there's the net amount of charge on this annulus, which would be a solid disk with a smaller disk taken out of the center. For part B now, it says that the annulus lies in the YZ plane. So there's Y, there's Z, here's the X direction. The center is at the origin for an arbitrary point on the x-axis, so some height here. Find the magnitude and direction of the electric field E. So let's go on to a fresh sheet of paper to start working this guy out. And we're going to use this idea again. So we know about the electric field of a disk. Let's ask, what are we going to do with our annulus? So we want the electric field of this object. So there's R1, here's R2, here's the solid part right here. We want this electric field. We know that this object equals a solid disk with radius R2. Take away a smaller solid disk with radius R1. So the net electric field is going to be the electric field of this disk. Take away the electric field of this disk. So let's find out what those electric fields are. The direction of the electric field, since it's a positively charged disk, is just straight up out of the disk. So I'm going to drop my vector signs. And we know that the direction of the electric field is away from the charged object. So let's write down what this guy is. Our result for a disk is that the electric field around a disk is the charge density divided by 2 times epsilon naught times 1, subtract the coordinate, how far away you are, divided by x squared plus the radius squared. And just so we don't get confused with our coordinates, let's get that on there again. So our x-axis points up, y-axis is to the right. Oh, there's our y-axis. So our z-axis is into the page. So we're trying to find the electric field at some distance x away. So we're trying to find the electric field at a point here, which is x away from the ring. And that's what we're trying to find. So on this guy, the x-axis points up, and on this guy, the x-axis also points up. The electric field and the direction of this electric field vector would be away from the disk. This electric field, same result here, but instead of R2, we'll use R1. So this is sigma over 2 epsilon naught, 1 minus x over square root of x squared plus R1 squared. So there's the electric field due to this disk. So the electric field of our annulus is the difference between these two guys. sigma over 2 epsilon naught times 1 minus x over square root x squared plus r2 squared. Subtract 1, subtract a negative gives us plus x over square root x squared plus r1 squared. 1 minus 1 gives us 0, and we're left with that electric field of the annulus equals sigma over 2 epsilon naught x over square root of x squared plus r1 squared minus x over square root of x squared plus r2 squared. Electric field is a vector, and the direction it points is away from the object. So the last part of our problem has us releasing a point particle with mass m and a negative charge. We're going to let it go and ask what happens. We'll do that in the next video.